When addressing whether a conveyor motor should be tied into an emergency stop circuit, several critical factors come into play. These factors encompass personnel safety, equipment protection, adherence to relevant codes and standards, and various operational considerations. In situations where the machine poses a hazard to personnel, it is imperative that the conveyor is stopped. This action aims to prevent further injury by halting the movement of materials or parts that could exacerbate the situation. Imagine a scenario where a worker is caught in a machine and the conveyor continues to feed materials into the area, intensifying the risk of harm. Equipment protection is also paramount. If the conveyor continues to operate while the machine is stopped, there is a risk of damage, particularly if the conveyor contains moving parts that could interact with the now stationary machine. For instance, a conveyor belt carrying heavy items might collide with a stopped robotic arm, resulting in damage to both. Compliance with codes and standards is non-negotiable. Many jurisdictions have specific regulations governing the use of emergency stop circuits in machinery. In the United States, the Occupational Safety and Health Administration, commonly known as OSHA, mandates that all machines have an emergency stop circuit that disconnects power from all motors, including conveyor motors. Other countries may have similar requirements, so it's vital to verify the applicable regulations for the specific location. Ignoring these regulations can lead to hefty fines and legal repercussions. Operational considerations also hold significance. While stopping the conveyor may impact other machines sharing the same conveyor system, as you mentioned, it is crucial to weigh this against the potential safety risks previously highlighted. Consider the overall impact of halting the conveyor versus the potential for injury or equipment damage. Material accumulation is another factor. If the conveyor continues to run while the machine is stopped, it may accumulate material, potentially increasing the risk of spills or other hazards. For example, if the machine normally processes items from the conveyor and it stops, the conveyor might overfill, leading to a messy and potentially dangerous situation. Process downtime must also be considered. Stopping the conveyor may cause a delay in the production process, and this should be factored into the overall risk assessment. A thorough analysis of the impact on production versus the safety benefits is necessary. Based on the aforementioned safety considerations, it is generally recommended to have the conveyor motor tied into the emergency stop circuit. This ensures that all power is disconnected from the machine when the emergency stop button is pressed, thereby protecting both personnel and equipment. This approach provides a comprehensive safety net in emergency situations. However, if specific operational constraints necessitate keeping the conveyor running during an emergency stop, alternative options can be explored. Firstly, you could install an independent emergency stop circuit. This would involve creating a separate emergency stop circuit for the conveyor motor that is not connected to the machine's primary emergency stop circuit. This allows the machine to be stopped while the conveyor continues to operate, if deemed safe. Secondly, consider using an interlock system. An interlock system could be implemented to prevent the conveyor from operating if the machine is stopped. This ensures that the conveyor only runs when the machine is in a safe and operational state. Thirdly, machine guarding is essential. Providing physical guarding around the machine to prevent contact with rotating parts while the conveyor is still operating can significantly reduce the risk of injury. This could involve installing barriers or cages to keep personnel away from hazardous areas. It is important to acknowledge that these alternative options may not meet the requirements of all codes and standards. Therefore, it is highly recommended to consult with an experienced safety professional to determine the most suitable solution for your specific application and to ensure compliance with all relevant regulations. They can conduct a thorough risk assessment and provide tailored recommendations. When evaluating these options, consider the following points in detail. Firstly, the specific hazards posed by the machine and the conveyor system. Analyze the potential risks to personnel and equipment in the event of an emergency stop. Secondly, the applicable codes and standards in your jurisdiction. Ensure that any chosen solution complies with all relevant regulations, including OSHA standards in the United States. Thirdly, the operational impact of stopping or continuing the conveyor's operation. Assess the impact on other machines and the overall production process. Fourthly, the cost of implementing different solutions. Compare the costs of installing a dedicated emergency stop circuit, an interlock system, or machine guarding. Fifthly, the maintenance requirements of each option. Consider the ongoing maintenance and testing required to ensure the continued effectiveness of the chosen solution. Emergency stop circuits are critical safety components in industrial settings. They are designed to quickly halt machinery in the event of an emergency, minimizing the risk of injury or damage. Understanding the principles and best practices for emergency stop circuits is essential for anyone involved in the design, installation, or maintenance of industrial equipment. An emergency stop circuit typically consists of several key components. Firstly, an emergency stop button or switch. These buttons are usually large, red, and easily accessible, allowing operators to quickly shut down the machine. Secondly, a control relay or safety relay. This relay monitors the state of the emergency stop buttons and energizes the machine's power supply when a button is pressed. Thirdly, wiring and connections. Proper wiring and secure connections are crucial for the reliable operation of the emergency stop circuit. Fourthly, a power supply disconnect. This mechanism physically disconnects the machine from the power source, ensuring that it cannot restart accidentally. The design of an emergency stop circuit must adhere to specific safety standards such as ISO 13850 and IEC 60241. These standards outline the requirements for the design, performance, and reliability of emergency stop systems. When designing an emergency stop circuit, consider the following. Firstly, the location of emergency stop buttons. Place the buttons in easily accessible locations within reach of operators and other personnel. Secondly, the type of emergency stop device. Choose the appropriate type of emergency stop device, such as a push button, pull cord, or foot switch, based on the specific application and the needs of the operators. Thirdly, the wiring and routing of the emergency stop circuit. Use proper wiring methods and ensure that the wiring is protected from damage and interference. Fourthly, the redundancy and fault tolerance of the circuit. Incorporate redundancy and fault tolerance to ensure that the emergency stop circuit remains functional even if one component fails. The installation of an emergency stop circuit must be performed by qualified personnel who are familiar with the applicable safety standards and the machine being controlled. When installing an emergency stop circuit, adhere to the following. Firstly, follow the manufacturer's instructions. Carefully follow the manufacturer's instructions for the installation of the emergency stop components. Secondly, verify the wiring and connections. Double-check the wiring and connections to ensure that they are correct and secure. Thirdly, test the emergency stop circuit. Thoroughly test the emergency stop circuit to ensure that it functions correctly and reliably. Fourthly, document the installation. Document the installation, including the wiring diagrams, component specifications, and test results. Regular maintenance and testing are essential for ensuring the continued effectiveness of an emergency stop circuit. Implement a schedule for regular inspection, testing, and maintenance of the emergency stop system. During maintenance and testing, firstly, inspect the emergency stop buttons and switches. Check for damage, wear, or corrosion. Secondly, test the operation of the emergency stop circuit. Verify that the circuit energizes the machine's power supply when an emergency stop button is pressed. Thirdly, inspect the wiring and connections. Look for loose connections, damaged wiring, or other signs of deterioration. Fourthly, replace any worn or damaged component. Replace any components that show signs of wear, damage, or corrosion. Emergency stop circuits are not a substitute for other safety measures such as machine guarding, interlocks, and safe work procedures. Emergency stop circuits should be used in conjunction with other safety measures to provide a comprehensive safety system. When using emergency stop circuits, firstly, train operators and other personnel on the proper use of the emergency stop system. Secondly, ensure that emergency stop buttons are clearly labeled and easily accessible. Thirdly, develop and implement safe work procedures that address the potential hazards associated with the machine. Fourthly, regularly review and update the safety system to ensure that it remains effective. Different types of emergency stop devices are available, each designed for specific applications. The most common types include firstly, push-button emergency stop switches. These are the most common type of emergency stop device, typically featuring a large, red mushroom-shaped button that is easy to press. Secondly, pull-cord emergency stop switches. These switches are activated by pulling a cord, making them suitable for long machines or areas where operators need to be able to quickly stop the machine from a distance. Thirdly, foot switch emergency stop switches. These switches are activated by pressing a foot pedal, making them suitable for applications where operators need to keep their hands free. Fourthly, wireless emergency stop systems. These systems use wireless technology to transmit the emergency stop signal, allowing for greater flexibility and mobility. Integrating an emergency stop circuit with other safety systems can enhance the overall safety of the machine. Some common integration strategies include firstly, integrating with machine guarding. Interlocking the emergency stop circuit with machine guarding ensures that the machine cannot operate unless the guards are in place. Secondly, integrating with safety controllers. Using a safety controller allows for more sophisticated control and monitoring of the emergency stop circuit. Thirdly, integrating with programmable logic controllers, or PLCs. Integrating with a PLC allows for the emergency stop circuit to be integrated with other control functions. Fourthly, integrating with remote monitoring systems. Using a remote monitoring system allows for the status of the emergency stop circuit to be monitored remotely. When selecting components for an emergency stop circuit, consider the following. Firstly, safety ratings. Choose components that are rated for the appropriate safety integrity level, or SIL, or performance level, or PL, based on the risk assessment. Secondly, reliability. Select components that are known for their reliability and durability. Thirdly, compatibility. Ensure that the components are compatible with each other and with the machine being controlled. Fourthly, ease of use. Choose components that are easy to install, maintain, and operate. The risk assessment process is a critical step in determining the appropriate safety measures for a machine, including the need for an emergency stop circuit. The risk assessment process involves firstly, identifying the hazards associated with the machine. Secondly, assessing the likelihood and severity of each hazard. Thirdly, determining the appropriate safety measures to reduce the risk. Fourthly, documenting the risk assessment. Understanding common pitfalls and mistakes when designing, installing, and maintaining emergency stop circuits can help prevent accidents and ensure the safety of personnel. Some common mistakes include firstly, failing to perform a thorough risk assessment. Secondly, using incorrect or incompatible components. Thirdly, improperly wiring or installing the emergency stop circuit. Fourthly, neglecting to test and maintain the emergency stop circuit regularly. By avoiding these common pitfalls and following best practices, you can create a safe and reliable emergency stop system that protects personnel and equipment.